from University Belfast, and what I'm talking about is a method to use supervised learning, a classical supervised learning approach to help solving a problem in quantum mechanics, in particular a gate design problem. So this means to find Hamiltonian, a time-independent Hamiltonian that generates a given target area, C0, hopefully, whatever. So this work was done in collaboration with Leonardo Banchi and Sugato Bose from Imperial College and University College London, and my supervisors Alessandro Ferraro and Mauro Paternostro. And this work builds on top of a previous work by Leonardo Banchi, Nicola Pancocchi, and Sugato Bose. So my starting point is really any circuit. Doesn't matter what this does, just a nice picture from Google. The point is, what you can very often find in such circuits are these guys. So let's say 3-qubit interactions, or 3-qubit gates, or similar kind of gates. So this in particular is a control not gate, so a TOEFL gate, as it's called. And the problem with these is that if you actually want to build these in a laboratory, say you want to do a TOEFL gate in your IBM quantum experience, it's not that trivial how to do it, because naturally these kind of gates require 3-qubit interactions. Okay, see, if you use time-independent dynamics. Now, the way they are usually implemented is either you decompose them using simpler gates, so you take a universal gate set, say C0 and Hadamard T gates, and you implement TOEFL as a series of these simpler gates. Or you use a time-dependent dynamics, so quantum control techniques or such. Or maybe use ancillary qubits or higher dimensional spaces, so maybe your actual physical system is a 3-level atom, and you actually implement the dynamics between qubits as an effective dynamics into a to the lower levels. But the problem is these are all kind of, say, workarounds, because so if you decompose the gate into a series of simpler ones, you increment the interaction time that is required. Of course, so if the device is not perfect, as it never is, the more gates you need in your circuit, the higher the noise and all of these. And then if you need to use ancillary qubits or higher dimensional hyperspaces, this of course requires a larger amount of resources. And quantum control techniques require that you're able to, do a very well-tuned time-dependent dynamics or things like that. So the question is, can we dispose of all of these techniques? So can we do a specific hard gate using a time-independent dynamics without decomposition and without using ancille and using only qubits, so without exploiting a higher dimensional dynamics? So in other words, this basically boils down to the problem of computing the algorithm of a matrix. Right, so I have my target gate, unitary gates in this case, and I want to find a time-independent Hamiltonian h such that the exponential of IH basically gives you u after a specific time. So I'm fixing the time, let's time t equal 1, because I can always say think of time as inside the parameters of the Hamiltonian, and ask, okay, I need to find a logarithm of u such that it satisfies some constraints. The constraints are, I want the Hamiltonian to contain all interactions that I can actually use and implement in the given experimental architecture. Okay? So the idea is to reframe this problem as so this is an optimization problem. The idea is to reframe it as an optimization problem over, say, sort of behaviors. So the idea is, instead of just optimizing a gate to do what I want, I think of the way the gate acts on a set of inputs, and I compare the outputs I get with the outputs I wanted. So this is very well suited for a supervised learning approach, because I can say, well, I take a bunch of, I start with random values for the parameters in the Hamiltonian, I take a bunch of random input states, I evolve them through the network I have, and I compare the outputs I get with the outputs I wanted. Okay? The advantage is, of course, I know the actual gate I want as a result, so I can generate as much, say, training data as I want. It's very easy, because we focus on, say, 3-4 qubit systems, or in general low-dimensional systems. And of course, we also have a natural model. We don't need to use, say, a neural network as a model, a universal kind of model. We know we want our model to be the physical one because we're actually looking for the parameters of the Hamiltonian. Okay. So once you frame it this way, you can just use the regular techniques that are used, for example, to train neural networks. The only difference is, well, you don't have a neural network, you have the qubit network, the set of qubits and the way the input states evolve through such a network. Okay, so what you do is, you parameterize the Hamiltonian in some way. Okay, you start with initial random values for the parameters of the Hamiltonian, and you generate a bunch of random input states, you evolve the input states, and then you do a gradient descent step, which means you compare what you get with what you wanted, and you go up the slope. Now, the problem with this is that in general, computing the gradient of a cost function, in this case, can be quite hard because the cost function is basically the fidelity between the output state we obtained and the output state we wanted. Now, the gradients of such a thing, I mean, it's not clear how to do it. So what we can do is to exploit well-tested and well-tuned algorithms that are used in machine learning communities that allow you to basically automatically compute the gradient of an algorithm, so to speak. So this is called automatic differentiation, and this allows you to, given the cost function of your model, which in our case is really the fidelity, the output fidelity, you write this function as a set of basically a set of elementary functions, elementary equations, which in this case elementary means that you know how to compute their gradients. So you compute you write this computational graph of an algorithm, and once you do that, these libraries can automatically basically compute the gradient as another algorithm. So you have a kind of analytical expression for the gradient expressed as an algorithm that you can efficiently compute. So this allows to do this step quite efficiently. So if you don't use this technique, you have to use instead numerical differentiation techniques that can be quite inefficient because, well, you have to differentiate with respect to a lot of parameters. Then you need to decide how to choose the step for the numerical differentiation, such things like that. Okay. So what you do is you use this technique, you do it a bunch of times, and at the end you get your result. When you get good enough fidelity, which in our case usually is like 1 up to numerical precision, so let's say a fidelity greater than 1 minus 10 to the minus 15, or something like that, and you get a good result, well, you're done. Okay, you have the parameters, so that you know that you got a bunch of parameters, and therefore Hamiltonian contains all the interactions you want that you can do with your experimental apparatus or whatever. The problem is with this is that, okay, this is a very black box approach. I'm not using at all the structure in the problem. So let's try to understand a little bit more what happens. So as an example, I consider the case of a TOEFL gate, and I'll ask the question, can I implement TOEFL gate with a time-independent dynamics without using any 3-qubit interaction? So using only basically 1 and 2-qubit interactions. So in practice, Pauli matrices or products of 2 Pauli matrices. Okay. So to answer this question, we basically compute the logarithm of this gate. So to do that, you write the gate in its spectral decomposition. It turns out that this gate has a 7-fold degenerate eigenvalue plus 1 and a non-degenerate eigenvalue minus 1. This is the spectral decomposition. When you take the logarithm, what you get is simply I pi P8. P8 is the projector onto the non-degenerate eigenspace. Okay? If you write P8 in terms of Pauli matrices to see what actual interactions are in there, you find that you have a bunch of 1 and 2-qubit interactions, which you don't care about for now, and that 3-qubit interaction term, which is kind of your problem because you're saying, I don't know how to implement this term directly the architecture I have. Okay, but so the question is this the only generator I can get? Of course not. Why? Because logarithm is actually a multivariate function, right? So there is not just one logarithm. So if I consider all possible logarithms, I have an expression like this, where nu1 and nu2 are integer parameters that I can choose any way I want. Okay? And something interesting can already be seen here because I can choose nu1 to be 0, and this means that my Hamiltonian will not have a ZZZ interaction. But whatever choice I make from nu2, I will always have a ZZX interaction. So from this it looks like you cannot actually dispose of these distributed interactions. But again, we're still being kind of naive because when we wrote the spectral decomposition, we didn't take into account that there is arbitrariness in which we can write the projectors into the degenerate eigenspace. Okay? So in particular, you can apply any unitary rotation of the degenerate eigenspace and obtain new projectors that are still fine for the spectral decomposition. So if you take the logarithm after this rotation, you get an expression like this. Now, there is a lot of freedom in this one because so you can choose the integer parameters any way you want, fine. But also you can choose the unitary rotation any way you want. And this means there are many continuous degrees of freedom. Okay? It's very hard to write now a general expression for this in terms of parameters because there's a lot of freedom. So the question is, can I use this freedom to get rid of all the tricubic interaction terms? So before trying to answer that question, let us see for a moment what it means to use this more kind of complex, it's less trivial Hamiltonian. So if you compare the actual evolution of the principal generator, this means the generator I got without taking into account the multivaluedness of the logarithm nor the degeneracy of the eigenspace of the gauge. And I compare that with, say, a general generator. So one I got taking a random unitary rotation and random values for the integer parameters. So if I do that, what I get is something like this. So on the left we have a very clean evolution. On the right we have kind of a mess. But at t equal 1, we get exactly the gate we want. Of course, we designed the Hamiltonian to just that, so it's not surprising that it does that. But the question is, can you exploit all of this additional freedom to get rid of Hamiltonian terms that you don't want because you don't know how to actually make them? So to answer this question, it turns out that this question is equivalent to another one, let's say. So even a target gate G, say a Toffoli gate or whatever else, and the principal generator Hg, I want to find another Hamiltonian H tilde, which only contains the physical interactions, which means the interactions are not to meet, and it commutes with the principal one, and it's such that the spectrum of that H prime is composed of integer multiples of 2 pi. So if these conditions are verified, and only if these conditions are verified, my new generator satisfies what I want. Okay? The first two conditions are very easy to verify because they're linear. The third one is kind of tricky because it requires you to compute the spectrum. Okay? So it's a mess if there are a lot of parameters. However, if I use, for example, the results I got numerically from my supervised learning approach as an ansatz, I can remove enough interactions, enough terms, to actually get analytical results. So for example, these are a couple of results we got. So for the Toffoli gate, it turns out that this particular Hamiltonian contains only 1 and 2 qubit interactions and perfectly reproduces the Toffoli after time t equal 1. So this means that you can just, if you know how to make these interaction terms, you just fix these values for the parameters, you wait this amount of time, and you get a Toffoli without using time-dependent dynamics or things like that. However, so this is similar result to the fracking. However, if I want to impose further restrictions, let's say I only know how to make not any 2 qubit interaction, but only diagonal 2 qubit interactions. So let's say XX, YY, and ZZ interactions. Can I solve for that case? So analytically, it turns out it's difficult. However, I can then use my supervised learning approach and get a bunch of results. So what I do is I use my analytical conditions to write an efficient parameterization for the Toffoli gate that only uses the interactions I want. And then I run the training over that model. And I can get a lot of results. So here, each line is a different set of parameters that implements Toffoli gate using only diagonal interactions, for example. Okay? And these are all achieved with basically fidelity 1 up to numerical precision. And then, okay, this kind of approach is very flexible, so you can do the same with Fredkin, get a Fredkin or diagonal interactions, or you can do basically the same with to generate any controlled unitary operation. So So U here is a 1 qubit gate, anyone. Or you can, I don't know, achieve other gates. For example, the half-adder gate, which is basically a Toffoli times a C0, in a particular way. Or you can also do this in a slightly different context in which you have more qubits, but you have some of these qubits as ancille, some of these qubits as let's say, your system qubits. You evolve in the whole network and you trace out the ancille at the end, and you want to implement a given gate on my system qubits. Okay? So in this case, in this framework, we can, for example, train for this what I call the two-threading gate, which means a control gate, which if the first qubit is 0, implements a NOT on the second 2, and if the first qubit is 1, implements a swap on the second 2. So it's kind of a mixture of Toffoli and threading gate. Or you can, for example, find approximate results for the QFT with 3 qubits plus 5 ancille, training over a couple of hundreds of Hamiltonian parameters, and potentially you can try really whatever you want, because once you have the framework, you can just plug in the target gate, you know this gate is interesting for whatever reason, and the constraints you want, and you can train the network. It won't work every time, it's not clear when it will actually work, but if it works, it's easy to check, because you have the values, just exponentiate the values, and see if you got the result you wanted. Okay, so to conclude, stochastic gradient methods can be very useful for these kind of problems, and probably the best thing about this is that the framework is extremely flexible. So in this case, we asked the network to implement unitary gates, but we can ask for more. We can say we can change maybe the fidelity function we are using as cost. If we want to optimize for some property of the network, maybe we want the gate that is the most entangling in this measure. Or maybe we can train over not unitary, say not non-unitary gates. We can train over maps, for example. Okay, this just requires a small change in the cost function we used. But the rest is basically the same. Why? Because the automatic differentiation basically allows you to complete the whole iteration automatically once you define how the training data is generated and what is the cost function. Okay. And then, of course, there are many open questions. In particular, when does it work? Why does it work for the Toffoli gate and the threading gate, and it probably doesn't work for the QFT gate? We don't use ancille. Okay, it's a very mathematical problem of trying to find looking into the logarithms of a matrix and looking for the ones that satisfy the conditions you want. Okay, and eventually you can do much more. So with this I conclude. Thank you very much.
Very much for the stuff. Any comments? Questions, please?
Have you seen any patterns so far between different possible decomposition and robustness against noise, or eventually do you want to introduce noise as a free parameter in the optimization?
So the first question is patterns in the solutions. You say, well, I mean, in some sense, sure, we found an ideal solution. So actually, this is just one solution and one solution. What actually happens is that you can solve these conditions, and what you find is a class of solutions. For example, the actual thing we have here is a class of Hamiltonian that generates the Toffoli gate that depends on 4 or 5 integer parameters, so it's an infinity of possible solutions. But if you ask, okay, starting from the numerical solution I got, so for example from here, find patterns from here, well, let's see, if I found the patterns, I can basically solve it analytically. So what will actually happen is that these solutions came because we found the patterns in the numerical solution, and we use those as answers. So in this case, yeah, sometimes you can, and when you can, it's kind of cool because you can find the solutions analytically, right? And second question is, of course, noise. So given the method we are using, which is a kind of local optimization, the solutions are basically stable with respect to a variation of the parameters, okay, of the parameters in the Hamiltonian. If you ask stability with respect to the time, so the time you evolve in the system, then it's basically the same thing, provided that the coefficients are comparable with each other, because to vary time means to vary all of the coefficients together. Okay? if you instead ask for the stability with respect to, for example, the coherence of one of the qubits, maybe one of the qubits is different from the other. And that's a very hard question because it will really depend, right? So Toffoli gate in this particular, for this particular solution, maybe it's slightly, we didn't study it, maybe it's slightly less stable, but it's still better than the composition you would have done otherwise. In another solution, we contain parameters that are larger, so maybe those are worse. It will really depend on the case, I would say.
One more last question. I think it's on this one.
Sorry. So it's about your last comment, saying that. So why is it not possible to kind of design some, say, analytical condition that says when it's possible to find this decomposition or not? It's hard for me to understand why. So.
Well,
why you don't know a priori, so you can maybe say,
let's say I would have before doing this, I would have expected that I would have expected there to be an answer to this question because it seems very elementary, right? Turns out that at least I couldn't find it. I asked around a little bit and I couldn't find it. The reason is probably because, well, one reason is probably that no one actually bothered to look into it. They didn't have a reason. And another one is that, okay, let's do here. It's not so trivial to look into this. Also, the constraints you're imposing are not are kind of arbitrary because you're asking for permutations such that this thing decomposed in a particular basis, which is the Pauli matrix basis, basically, satisfies this and this requirement. It's not so trivial, so I couldn't find a solution at least, and I couldn't find any solution looking into it. So I did look because I expected there to be a solution.
All right, let's thank once more.